Sharma, and today we're going to be doing the first video on this channel in the series for learning machine learning and deep learning. And so today's video is Machine Learning Intro and Applications. This is the first video in this series, and there will be approximately 20 videos for which you can use to learn machine learning and follow along with this course. So let's get started. So let's start off by talking about what is machine learning. Machine learning is the study of algorithms that improve the performance P at some task T with experience E. In this case, there's always a well-defined learning task PTE. And so in this case, we want algorithms that can improve their performance P at some certain task T, right, with experience E. So what's a real-life example of this? So let's just say we want a machine learning application or algorithm to be able to detect spam emails versus not spam emails and basically classify them. So what's the performance in this case? The performance is how good they are at actually physically classifying emails as spam or not spam. The task is the action of classifying emails as spam or not spam. And experience is how many emails in the past that the algorithm classified as spam or not spam. So this is what consists of a well-defined learning task. And machine learning algorithms like the spam or no spam detection filter are all about improving the performance P at the task T with experience E. So it's important to differentiate machine learning from traditional programming. In traditional programming, there are two inputs. There's a data and a program. These go into our computer and they spit out an output. In machine learning, however, we input data and the output into our computer and we get out a program. So what this means is that unlike traditional programming, machine learning is all about creating an algorithm that can be used to predict future outputs. So in machine learning, therefore, it is necessary to give our computer or model an output to start with. So when do we use machine learning? Machine learning is used when human expertise does not exist. For example, navigating on Mars. Another example is when humans cannot explain their expertise, for example, in speech recognition. Machine learning models must be extremely customized. For example, in personalized medicine, there must be an individual machine learning model for each patient at a certain hospital or clinic. And furthermore, machine learning models are heavily based on large amounts of data. For example, in genomics, where we navigate the human genome using machine learning algorithms. When is machine learning not useful? When there's no need to learn to calculate payroll. Here's some more examples of tasks that are best solved by using a learning algorithm. For example, recognizing patterns. This is a very broad task, and there are lots of subtasks that qualify under the idea of recognizing patterns. For example, facial identities or spatial expressions, recognizing handwriting or spoken words, or medical images. These are all tasks that our algorithm is trying to recognize a pattern or a certain trend. The next example is generating patterns. In this case, an example is generating images or motion sequences, or human faces that never existed. These can be solved with special machine learning and deep learning algorithms such as GANs, generative adversarial networks, which we'll talk about in the later videos in this series. Another example of a task that machine learning algorithms can do is recognizing anomalies. For example, an unusual credit card transaction is a clear anomaly from the rest of the credit card transactions, and a machine learning model can recognize the trend and figure out outliers from the trend, like an unusual credit card transaction. And last but not least, probably the most common use for machine learning algorithms is for future prediction. And this is not extrapolation. This is more like the kind of prediction where we're predicting a certain output Y based on input X. So for example, predicting future stock prices or currency exchange rates. So in essence, these are all examples of tasks that are best solved by using a machine learning algorithm. So let's move to the types of machine learning that we will talk about throughout the series. The first type of machine learning is supervised or inductive learning. Supervised learning is where an algorithm uses training data and feedback from humans to learn the relationship of given inputs to a given output. For example, how the inputs, time of year, and interest rates can help us predict housing prices. So in this case, our givens are training data and desired outputs, which in other words are our labels. Next is unsupervised learning. Unsupervised learning is when an algorithm explores input data without being given an explicit output variable. In other words, you're exploring the data without desired outputs. An example is when we're basically exploring customer demographic data to identify patterns. That's an example of unsupervised learning, because we're only giving training data and we do not have our desired outputs or labels. So this is more of a process where it's not as clear as to how to map out the algorithm. And that's why unsupervised learning is more difficult than supervised learning. Because in unsupervised learning, we have to try to create the actual algorithm without any output knowledge. Next is semi-supervised learning. This is kind of a hybrid between supervised and unsupervised learning. But in this case, semi-supervised learning is where our given is training data and a few of the desired outputs. Not all of them, and not zero desired outputs. And last but not least, reinforcement learning is a really popular type of machine learning that's becoming more and more popular these days. And reinforcement learning is where an algorithm learns to perform a certain task simply by trying to maximize rewards it receives for its actions. For example, an algorithm can try to maximize the points it receives for increasing returns on an investment portfolio. And so therefore reinforcement learning is really popular because it takes ideas from game theory and rational behavior and applies it to machine learning agents. And the overall idea is that we are providing rewards from sequences of actions that are desirable. So let's differentiate on some of the algorithms on the supervised learning side and the unsupervised learning side. So supervised learning is a much broader field for now, and the algorithms that it uses are like in decision trees, which are a certain classifier, linear regression, logistic regression, support vector machines, kernel methods, Bayesian learning, neural networks and deep learning, etc. Unsupervised learning is still a developing field, and it's not as popular as supervised learning, but the research in unsupervised learning right now is currently under clustering and dimensionality reduction, which we'll talk about in later videos. And currently, reinforcement learning is becoming extremely popular, and Q-learning and SARSA are some very popular reinforcement learning techniques. We will discuss them in a future video. So let's jump into supervised learning. So supervised learning is all about having both inputs and outputs. So in supervised learning, we can have a multidimensional X, or multidimensional inputs. Each dimension corresponds to an attribute, or a certain feature. And in this example, or case study that we're going to use for this video, we're going to talk about malignant versus benign tumors. And so in this case, these are some of the X's or features that we use in our model. In this case, how thick is the clump or tumor, the uniformity of cell size, and the uniformity of cell shape. So let's just think about an unsupervised learning approach. In unsupervised learning, we're given x1, x2, xn without labels, which are our inputs, and we want to output hidden structures behind the certain inputs. And so this is clustering. So as you can see in these graphs, we basically see these, as the human brain can clearly differentiate between these three groups. But it takes a bit of intuition for a machine learning model to be able to cluster these input variables without any output structure. So what are the applications of supervised learning? Supervised learning is really popular because, once again, it's pretty useful in clustering applications and more of analysis. And so, for example, organizing computing clusters, social network analysis, astronomical data analysis, market segmentation. These are all developing applications of unsupervised learning. So let's talk about more about applications before we dive into more of the technical information that you need to know for machine learning and supervised learning. So I believe that these days in the headlines you see how pervasive deep learning has become. So all these headlines you can see that deep learning is more than a buzzword. As Andrew Ng put it, deep learning is the new electricity, right? And it's important to realize that deep learning is definitely power, but it's a responsibility as well, because humans really need to be able to navigate the prospects of deep learning without abusing it or not letting it advance at the right rate. So deep learning is definitely a tool for great social power, but we also must use it very carefully. Let's talk about some applications of machine learning. So in practice, machine learning can be used for a lot of practical computing tasks. For example, mining databases, control learning, control theory, speech recognition, object recognition, text analysis. The possibilities are completely endless. Here's some more sample applications for machine learning and deep learning models. Web search, computational biology, as we talked earlier with genomics, finance, stock prediction, e-commerce, space exploration, robotics, information extraction, social networks, and as you can see, your favorite area, machine learning has applications in nearly every field possible, whatever you want. Let's talk about one specific application, autonomous car technology. So how do these self-driving cars work? So they have a system known as LiDAR. And LiDAR is really that system that sits at the top of these self-driving cars, as you can see in this image. And LiDAR is one of those mapping technologies that collects data for self-driving cars. As you can see in the example at the top left of the screen, you see a laser terrain mapping technique. And what these cameras and high visual processors are doing is that they're basically mapping the surrounding terrain in order to collect data on it. Why is this important? Because in the future, companies like Google and Uber and Lyft, they want to collect as much data they can before they release self-driving cars on the market. This is because they want to make self-driving cars as safe and efficient as possible. And without mass data to study and analyze, that's just simply not possible. Moreover, there's some more advancements in the field of autonomous car technology. For example, path planning or adaptive vision, or even just learning from human drivers. These are all challenges and up-and-coming developments in the field of self-driving cars. Here's another interesting case study: the use of deep belief net on face images. So, deep belief net is a very popular facial recognition neural network, and what it's trying to do is that it's basically taking an input image and stretching it to look at the object models in that image. And this network is an example of a top-to-bottom computer vision deep learning network. And as we'll talk about in later videos, computer vision and convolutional neural networks are some of the most popular fields in machine learning and deep learning today. And without them, we can't do any of the computer vision or image analysis or object recognition that we do today. Here's some more really interesting applications of machine learning. Learning prosthetic control from neural implants, learning to classify a word a person is thinking about based on the fMRI activity, learning to detect objects and images, a very popular application, learning to classify text and documents, and learning to predict emergency C-sections. So as you can see, literally any area can have a use for machine learning. So now let's get a little bit more technical and talk about some of the interesting machine learning terms that you might want to know. So it's very important to realize that machine learning is completely built on data. Without data, machine learning simply can't happen. Every kind of machine learning model requires an input data, or X features. And why is data so important? And so I have a question for the audience, and the question is that, why do you think machine learning is becoming more popular in the 21st century? Why now? Because some of these technologies have existed as far back as the 1960s, right? Where the first neural networks were thought of, or some of the first computers were at the heights. So why now? And take a moment to think about that, but I'll just give you the answer. Feel free to pause the video. But the answer to that question is because today we have compiled so much data that high-scale machine learning is possible. Without all the data that's collected in repositories and datasets online, we simply cannot do machine learning. And thus, the starting point of machine learning is the data. And that's why today in the 21st century, machine learning is finally able to really move to the next level. So for now, we're going to focus on supervised learning. And as we talked about earlier, supervised learning is the example where data is provided with both inputs and outputs. In contrast to unsupervised learning, which only provides inputs. A supervised learning example, also called a data point or instance, is simply an input-output pair, x, y, which specifies that y is the ground truth output for x. The training data is a multi-set of examples. What I mean by multi-set is simply just a completely expanded list of examples. Repeats are allowed, but that's not the main idea here. The main idea is that it's basically a partial specification of the desired behavior of a predictor. What's an example of a training set in a machine learning model? Once again, heading back to the spam, no spam example. In that example, we talked about how we should have a machine learning classifier that's able to distinguish spam emails from not spam emails. In that case, the training data, multi-set of examples, in that problem will simply be a set of data where basically we have spam and no spam emails that are already classified as spam or no spam. In other words, we basically have a collection of emails that are already been classified as spam or not spam. Why is this essential to the model? Because with these examples, we can have our model recognize the trends in those emails to see which emails they should really classify as spam or not spam. And that's why training data is so important. It lets our model really recognize patterns and distinguish what features are important. So let's talk more about data. So heading to the most basic definition of data, or an example pair. An example of data is where one specifies that y is the ground truth output for x. And this forms a pair, or example, xy. And we usually write this in function style notation where we have xy. And what is our training data then? The training data is simply the list of examples that our model incorporates. And so as you can see here for dtrain, we see that this is just a list, it's an array of these xy pairs. So let's talk about more important machine learning vocabulary. So we know the terms are features, labels, models. So we've already brought these terms up, but let's go a little deeper into them. So labels are the things we're predicting, the y variable in simple linear regression. Features are the input variable, the x variable in simple linear regression. Models is what defines the feature between features and label. To train the model means to create or learn the model. In other words, show the model labeled examples and enable the model to gradually learn, or identify patterns, or recognize trends. Inference means applying the model to unlabeled examples. What do I mean by an unlabeled example? An unlabeled example is where we only have x, not x and y. And thus, we want to be able to apply our model to an example where we don't know the output, and see what the output is from the model. And this is the general way a machine learning model works. As you can see in the diagram below, we have a certain input, we have a certain model parameters and function h of x, and we're able to attain an output y. So you can really just think of a machine learning model as a mathematical function. F of x equals our output y, where x is the input, f is the function or model, and y is the output. For this function analogy, you can also think of the x as the input or the features. You can think of the function itself as the model, and you can think of the output y as a label. So it's really important to realize this relationship between the features being plugged into a model to give a label. That's the schema of every machine learning model. Let's talk about a really crucial mathematical concept that's necessary to understand how machine learning models work on a mathematical basis. So we have a very important term known as a feature vector. What is a feature vector? A feature vector is simply a vector or a list that is a list of all the features or inputs that we need for our model. And so let's go back to our spam or not spam example. So in this chart in the middle of this diagram, you can see some of the features that are important to this model. So some of the features we have currently are the length, is whether the length is greater than 10. Does our email contain @ Does it end with .com? Does it end with .org? And also the fractive alpha. So these are our 5 features for this model. And for each of them, we basically give it a value. So for yes or no questions, we can basically say 1 or 0, where 1 is yes, 0 is no. So that's why this is how we get this feature vector 1, 0.85, 1, 1, 0. This is basically turning each feature into each of our features into one total vector that holds all the features. And the idea here is that each feature vector is an unlabeled example. And so the mathematical definition here is that for an input x, its feature vector is the summation of all features in that set. And in this case, we can think of our feature vector as having a dimension r in a high dimensional space, where the dimension is based on the number of features itself. So let's do a simpler machine learning example. Let's just say we want to classify between cats and dogs, and we had 2 features. Let's just say the features were the color, and the other feature was the tail size. And so for this example, we would have a feature vector of dimension 2. Why? Because we have 2 features, and we can represent each example as a 2-dimensional vector of features. So let's talk about another crucial part of the machine learning process, feature extraction. So in the example task, we want to predict whether a string x is an email address. And so one crucial question that you may be thinking about is, how do we know which features are relevant to our model? Or in other words, what properties of x might be relevant for predicting y? Because in the spam, no spam example, when we want to distinguish spam emails from not spam emails, there really is so many different possibilities for what could be considered a feature. It's very arbitrary and broad. And the whole point of feature extraction is to boil that down to something more concrete and something that can really help us to distinguish spam versus not spam emails. So this is where the feature extractor comes into play. The feature extractor is when we have a given input X and we output a set of feature name, feature value pairs. In other words, XY pairs. And thus, we run a feature extractor on every machine learning problem to find which features are relevant. And back to the cat versus dog example, when we classify between cats and dogs, we should definitely run a feature extractor to see which features are not arbitrary and are definitely useful for determining whether a given image is a cat or a dog. And in that case, we could probably get better features, something better than just what the color is or how long the tail is, something like the whisker length or something like the patterns of fur, etc. So that's what feature extractor does. It basically allows us to have insight into which features are the most relevant and most useful for predicting our output ground truth label Y. So this is a very important slide because now we're going to talk about the types of prediction tasks. And this is really important because all machine learning problems in a single dimension can be boiled down to one of these two, either binary classification or regression. So let's break this down. Binary classification is when we're basically predicting for discrete output. What does this mean? In other words, the spam email classification example is a binary classification problem because in that case we have two discrete outputs. The email can either be spam or not spam. In the other case, regression is a much more continuous problem. In this case, in regression, we're outputting a continuous value. Like if you're predicting housing prices in the Bay Area, then a regression algorithm will be able to predict the price as a continuous value, or in other words, a quantitative number. And that's how regression works. So the key differentiation here between these two is that binary classification relies on discrete outputs versus regression relies on continuous outputs. Here's some more deeper types of prediction tasks. So there's multi-class classification. So we have Y as a category. For example, we give it an image, and the goal is to predict whether it's a cat or dog. Then we have ranking, where the output is a permutation. 1, 2, 3, 4, we plug out 2, 3, 4, 1. That's the ranking algorithm. Then we have structured prediction. Y is an object which is built from parts. So we can either reorder it or mess around with the syntax, whatever you want. So we can turn La Casa Blue into the blue house through our function for structured prediction. So these are some more advanced prediction tasks, but the general schema is the same, where we either get some continuous output or a discrete output. And the important thing to remember is that, going back to this, binary classification, or just classification as a whole, is all about discrete outputs. That's why you can see here, 1 minus 1, yes, no. In the other case, regression is all about continuous outputs, like housing price, like stock market predictions, a continuous output of the nth dimension. So let's dive a little deeper into these regression and classification algorithms. So what is regression? So in statistics, you may have heard of the term linear regression or logistic regression. And so we're going to be talking about linear regression. And so linear regression, with like any supervised learning algorithm, relies on labeled examples. Labeled examples are input-output pairs, where we have both the input and output. And the goal of regression is to learn a function, f of x, to predict y given x. So y is real valued, or in other words, continuous. It's a quantitative number. So therefore, it's a regression problem. And as you can see in this graph, we're basically mapping input to output and forming a regression line. And in this regression line, we can basically predict for future output. That's how regression works. Here's a better example of how regression might appear to work. So we have a data set of all these points, right? We maybe want to extract a value for a point that's not shown on the graph. So the way we would do that is we would fit a line, and we would predict, based on our line or function, what another input x would be and what output it would give. So this is the intuition behind linear regression. Here's something a little extra. This is how the minimization of the cost function for linear regression. You don't really have to know this, but this is just something interesting, where we can think of regression as a cost function, and we're trying to minimize our cost, or in other words, our loss. We will talk about this more in the future lecture, but for now it's just important to understand that the goal of regression is to basically fit a line to a certain data set and be able to predict future output based on new inputs. And remember, regression is a supervised learning algorithm where we have both input and output, XY pairs for both. Let's talk about supervised learning classification. So supervised learning classification is where we're once again given labeled examples, input-output pairs, and we learn a function f of x to predict y given x. In this case, y is categorical, and this is y's classification. Categorical means the same as discrete. It's a categorical value, right? In this case, going back to our breast cancer example, where we're predicting whether a tumor is malignant or benign, remember, we're predicting between two categories. It's either malignant, 1, or benign, which is 0. So this is completely categorical and discrete. There's no continuous values going on here. So therefore, it's a classification problem. And we're given both input and output pairs. And as you can see in this graph based on tumor size, which is our x-axis, we can map to either 1 or 0, which is malignant or benign, based on our tumor size, which is on our output graph. So let's go back to the first application of spam classification, and let's talk about this. Let's break down this problem. So in spam classification, we have an input x, which is our email message. The output can either be spam or not spam. What's the objective of this problem? The objective is to obtain a predictor f, or a function that can help us to basically distinguish between spam or not spam. That's what the classification algorithm is trying to do. So here's some practice. For the following tasks, let's predict whether each is a regression or classification task. Number 1, predicting stock market prices and investment strategy. This is completely a regression. Let me explain why. Stock market prices are a very continuous quantitative output. A price is a number. It's a number, right? It's continuous. Therefore, it's regression because the output of a stock market price predictor will be the price, right? And if the price is a continuous output, therefore this problem is regression. There we go. Number 2, predict the type of color an object is. This is purely a classification task. You may be wondering why. Let me explain. When we predict the color of an object, then we're predicting a category, right, for this object. This is completely categorical. A categorical output is also a discrete output. Back to the breast cancer example of malignant versus benign, predicting the type of color an object is very similar to predicting whether a tumor is malignant or benign. They're both classification tasks because both of the outputs are discrete or categorical in essence. Number 3, predicting the ACT scores. Well, the ACT score is very similar to a number. It's continuous, it ranges from 1 to 36, and it is also quantitative, right? It's a number. Therefore, this is a regression example where we're predicting the ACT scores. This is a regression. Number 4, predicting the grade of a student based on preparation. Once again, this is also regression because the grade of a student is a continuous output or quantitative output. Thus, this is regression. And last but not least, number 5, predicting the processing speed of a device based on its specs. This is also regression because the processing speed of a device is a continuous value. And based on the specs are our features, the output itself is the processing speed, which is continuous. Therefore, this is also regression. And hopefully you found this practice pretty useful to validate your skills for distinguishing between classification and regression. And let's finish off. Let's conclude today's video by talking about by reviewing some of the stuff we went over. So let's go back to our applications of machine learning. Why is machine learning already the preferred approach to speech recognition, NLP, computer vision, robot control? Why? So one question for you to think of after you're done watching this video is that the machine learning niche is growing. And why is it growing? We have to really understand why it's growing. Let me answer this question for you. The machine learning niche is growing because, as we talked about earlier in the video, it's all about data. Today, data is becoming more pervasive and more accessible to the population, for machine learning engineers to data scientists, etc. Since we have access to more data, our computing technology is also becoming much more powerful, right? You're having like NVIDIA GPUs. We have some of the fastest processors ever made. So therefore, with this rapid acceleration in computing power and the amount of data we have, machine learning is becoming a really popular approach because we have the tools to successfully build really strong algorithms. Therefore, machine learning is growing into a niche today. let's talk about machine learning in a nutshell before we end the video. So there are tens of thousands of new machine learning algorithms every year. And we're going to talk about this in the third video of this series, but it's important to recognize that every machine learning algorithm has three components: representation, optimization, and evaluation. What do these mean? Representation is how the model is represented in terms of its input and outputs and its features and labels. Optimization is how we minimize the loss or increase the accuracy of our model. And evaluation is how we determine how our model really performs in the real world. We talked about this earlier when we discussed inference, right? Evaluating our model is applying our model to unlabeled examples, or examples where we don't know the output. These are the three major components of every machine learning algorithm. And so just a final review of what we did today. We talked about machine learning applications, supervised and unsupervised learning. We talked about machine learning models, notation, feature vectors, data representations, and functions. And we finished off by discussing regression and classification and the difference between these two machine learning algorithms. And make sure to think about these review questions in preparation for our next video, which will go more deeper into the idea of loss and accuracy that we touched upon in this video, and also go really deep into gradient descent, which is one of the most important machine learning optimization algorithms that exist today. And so these three review questions should be great preparation for next video. And thank you. That's it for today. And be sure to subscribe and drop a like if you enjoyed the video. And I will see you next time. Thank you very much.